Hi guys, welcome back to the channel. So today we are going to be solving today's lead code question, which is minimum height trees. So we are given a undirected graph and then it will not be consisting of any cycles. It is kind of like a tree, and then we need to find minimum height trees which are present in this particular tree. Suppose let's say we are given edges and then we are given the number of vertices present in this particular undirected graph, which is kind of like a tree, but it doesn't contain any cycles, and then we are given edges which is 1 0 and then 1 2 and then 1 3. So if we see, there can be four possibilities. One possibility is this, and then second possibility is this, and then third, and then fourth. Now if we see these particular possibilities, we need to find the minimum height trees. That means, suppose let's say if we consider 0 as root, then the height will be 1 and then 2. So this height will be 2, and then if we consider 1 as a root, then the height is going to be 1. And then if we consider 2 as a root, then we'll have 2 as our height. And if we consider 3 as our root, then we'll have the height of 2. So that's why we need to consider only this particular case where we'll have 1 as a root, and then we'll return this particular answer. Suppose let us take one more example where we have 1 0 1 2 and then 4 5. If I consider 0 as my root, uh, then the height is going to be 1 2 and then 3. And then if I consider 1, it is going to be same, and then for 2 it is going to be same. And then if I consider 3 as my root, then the height is going to be 2. And then 4 if I consider, then the height is going to be 2. So 2 is the maximum height minimum height we can make, so that it will have the minimum height for this particular tree. That's why we are going to return 3 and 4 as our answer. So suppose if we take these examples, we need to find the roots of this particular tree such that we'll have minimum height which will be present in this particular tree. And then if we come to the first approach, suppose let's say we want the minimum height which needs to be taken. uh, we can consider different possibilities. Suppose let's say I consider 0 as my root, and then I'll connect to all the nodes by taking 0 as my root. Then if I do that, then it is going to be like this: 0, and then it is going to have 3, and then it is going to have 1, and then 2, and then 3 is going to have 4, and then it is going to have 5. So this is going to be one possibility where we have 0 as our root. Now the height becomes much more. And then if I consider 3, it is going to be like this, and then height becomes 2. And then if I consider this, it is going to be height of 2. So there can be different possibilities. If I consider one node as my source, and then if I calculate the distance between this node and then this node, and then again I'll calculate the distance, and then again I'll calculate the distance. Suppose for this I'm going to get as 1 2 and then 3. So after taking each node as my source node and then calculate the distance, I need to do the traversal for n times. That means I'll consider n nodes as my source, and then I'll calculate the distance. For calculating the distance, we are going to use BFS. So that's why it is going to take n is the number of nodes, and then E is going to be the edges. So this will be the time complexity if I consider each node and then calculate the distance between that particular node and then all other nodes which are present in this particular graph. So if we come to the constraint, then we can see that here it has 10 power 4. That means if I multiply 10 power 4 with the 10 power 4, then it will not be possible, which will be solved in this particular solution. So that's why we need to optimize this particular solution so that we can solve this particular question. So that's why we are going to change our approach so that we'll get the answer in our state. So what we are going to do is we are going to observe the scenario and then we'll try to figure out the answer. So for this case, if I say that I'll take a graph. Suppose if I take this particular graph, I'll take this graph and then let us stretch this particular graph. Suppose let's say I have 0, 1 and then 3 and then 4 and then 5. So let us stretch this particular graph. So if we stretch it, it is going to be like this: 0 and then 1 and then 2, and then it is going to have 3, and then it is going to have 4, and then it is going to have 5. So suppose let's see, if I consider 5 as my answer, then it is going to be the maximum height is going to be 1, 2, 3. So for this it is going to be 3. Suppose if I consider this, the distance is going to be 2. The maximum height for this node, if we consider it as root, then it is going to be 2. Why? Because this side is 2 and then this side is 1. And then if I consider this as well, it is going to be the distance of 2. And then if I consider this, then it becomes a distance of 3. So if we observe this particular distances, here the distance is more, and then here the distance is more, and then whenever we move from leaf node to inside node, then we can say that this distance will be decreased. That means we are going to consider the middle node which is present in this particular graph if we stretch this particular graph. Suppose let us think, instead of taking all the nodes, let us say we have only one, we have nodes connected like this. Suppose if I take this, then the distance becomes more. If I take this, then the distance becomes less. So that's why we are going to consider the middle element. So what we are going to do is we are going to start from the leaf nodes, and then we'll try to traverse inwards. And then whenever we are traversing inwards, we are going to take all the nodes which are like at the middle of this particular nodes. Suppose if I consider here, I'm going to consider 0, 1, 2 and then 5. And then I'm going to move inwards. And then I'm going to get 3 and then I'm going to get 4. And then we have traveled already 3 elements and then 4 element, and then we are going to add 2 more elements which will be equal to total size of this particular vertices. At that time we are going to stop, and then we are going to return the 3 and 4 in this particular answer. So that's how we are going to do. We are going to take the leaf nodes, and then we are going to travel inwards, and then we'll get to the middle, and then whatever the middle elements which are present, we are going to take that as an answer, and then we'll return that particular answer. So let us see the solution for this. So what we are going to do is we are going to take adjacency vector which will consist of nodes and then these adjacent elements. Suppose let's say the number of nodes is going to be 1, then we are going to return 0 as our answer, and then there can be different edges. That's why we are going to add edges in this particular adjacency list, and then we are going to count the number of nodes which are traveled, and then we are going to check if this particular node is leaf node. Leaf node in the sense, if I consider, let's say I have one neighbor, I have one neighbor, that means that that element is going to be leaf node. That's why we are going to add to this particular leaf node, and then whenever we are done with this particular leaf node, then we are going to remove these edges which are present between 3 and then 0, and then we are going to remove from 0 to 3, and then we are going to push, and then we are going to increase size to here, and then we are going to pick the top element which is present in the queue, and then we are going to pop, and then we are going to check each adjacent element, and then from that we are going to erase this particular element. Suppose let's say I have one more one more connected element which is 7, and then it is connected to 0. Now this is the element which has 0, only one element, only uh, leaf node. We are going to move inwards to this particular 0, so that this particular node edge is going to break, and then we are going to travel to this particular 0. So that's what we are going to do. And then if the size of this particular adjacent element is going to be 1, then we can say that this particular adjacency element is going to be leaf, and then we are going to push this particular leaf. And then whenever we come across any count plus q dot size equal to is not equal to none n, then we are going to travel. If it is equal to n, then we are going to come out. Why? Because we have found this particular middle elements which is present, and then we are going to take all the elements which are present in the queue, and then we are going to push into our answer, and then we are going to return the answer. Yeah, that's all for this video. Thanks for watching the video.